Hi everyone, welcome to this series on feature selection methods. In this video, I'm going to cover one of the method under filter category, essentially univariate feature selection method. In the previous video, we looked at t-test as one of the methods to conduct univariate feature selection. In this video, I'll show you how to do one more method called ANOVA method. ANOVA is an extension of t-test. As you recall, t-test was between two groups. So since this is an extension, so ANOVA would be able to deal with more than two groups. And this is also based on variance, and in fact, it's called analysis of variance. So what is ANOVA? Is basically a statistical method to compare the means among more than three or more groups, whereas t-test was only for two groups. It allows you to assess whether there is any variability in the data, and that variability of data can be attributed to group difference or it is due to random fluctuations. So there are two different variations of ANOVA. So the first one is to compare. A one-way ANOVA is to compare essentially the means of one factor. So that means, for example, we have one categorical independent variable or factor, and there are multiple groups within that categorical variable. For example, it could be diet type, and it could be having different categories A, B, C, and you would like to assess the impact of diet type ABC on weight loss or weight gain of the individual. So this is called one-way ANOVA. Two-way ANOVA, on the other hand, is two categorical variables, let's say diet type and also exercise type or exercise level. And combining these two categorical variable, you want to see if there is any impact on the measurement called weight loss. So essentially, ANOVA is about variability, and it breaks the variability of data into two different types. So one is variability within the group. Let's say group is ABC, is going to compute the variability within the group, and the other one is variability across the group. And then you're going to combine both of these metrics together to come up with the final assessment. So let's take a look at an example here, exam score in different teaching methods. Let's say you have more than two teaching methods. In the t-test, we had only provision for two teaching methods. Here is more than two, like three or four or five different teaching methods. So in this example, we have three teaching methods and exam scores are collected for these three teaching methods. Let's say we apply these teaching methods on different set of students. The goal is to now check if the differences in the exam score exist in the teaching methods. Pretty much similar to t-test, only differences here we are considering more than two groups. So variability within the group, so this represents the variation in the exam score within each of the teaching method, like let's say A, B, C. And why do we do so? We'll try to understand the intuition behind the variability within the group. So for example, here the group A, students may have different study habits. So the students in the group A could be having different behavioral pattern, study habit, or the knowledge before, or ability to understand faster or slower, whatever it is. So this is about diversity within the group. So that's the variability within the group. So how do we compute this? It is calculated by assessing the variance. So this is pretty much the same. If you look at the formula here, this is for a group or individual value, and this is the mean of that particular group. So what you're going to do first is So the K is the number of groups, Ni is the number of observation, and in the ith group, and Xi is for that group, that observation, and Xi is the mean of that particular group. So first we compute all of that, essentially to find out how much is the deviation of each of the point from the mean of that group. So the step number one that we do here is to compute the mean of each of the group. Let's say A, B, C. For each of the group, you're going to compute this mean and then subtract the mean from the individual observation, square the deviation, and after that sum the deviation, and then sum of the square deviation across all the group. Means you're going to add them, add all of the deviations here. Okay, so let's take one worked out example here. Let's say the group is A, B, C, and these are the scores. The first step is to compute the mean of each of the group. Let's say 87, 80, and 90. These are the mean of each of the group. Then we compute the overall mean here. And after that, we compute the mean, the deviation within the group for each of the point and square them up and finally add all the variability within the groups, group A, B, C. So what's the intuition behind the variability within the group? It actually measures the spread or dispersion of the each of the individual data points within the group from the respective mean, and this also reflects the diversity of data or heterogeneity within the group. That's the intuition of finding the variability within the group. Now the next one is variability between the groups. Now we are comparing the differences in the mean between the groups here. Okay, so here more or less the same, just the difference is we're going to also compute the mean of all the groups together. So here the first step, overall mean, and then find out the difference from the overall mean for each of the group, square them up, and then we add them. And finally, sum the weighted square differences each of the group. Basically, number of samples, you multiply the number of samples from each of the group. And that gives you the weighting. Worked out example, again the group A, B, C, and we compute the group means and after that overall mean, and use the overall mean here from the respective mean within the group, let's say 87, and yeah, let me show you. So this is 87 here, and this is 85, and likewise 80 is here, and this is your 85 points, and likewise the same thing, and square them, multiply here by the number of samples. The number of samples is 5 in each of the group in this example. And after this, we'll look at the intuition behind the variability between the groups. So here we're now intending to find out to what extent the means of the different groups differ from each other. Intuitively, it measures the influence or the impact of the factor being studied. So, for example, weight gain or weight loss, and you're looking at multiple factors. These two combining, you're going to get the final result of ANOVA, pretty much the same. You're going to get the test statistic and also the p-value. There are assumptions in this ANOVA, pretty much the same like t-test, homogeneity of variances, normality of data, and independence. If these conditions are violated, then the results may not be reassuring. So you may have to consider these assumption points as well. There are variants of ANOVA. One-way ANOVA, we talked about it. Two-way ANOVA, also we talked about it. And there is another one, multivariate analysis of variance, is called MANOVA. We're not going to cover this in this particular video, Next, I'm going to show you the Python example to showcase the functioning of ANOVA and how do we infer from the results of ANOVA. Let's look at an example here based on the dummy data. So first one is going to be a one-way ANOVA. So for example, here the 4 columns, strength 1, strength 2, strength 3, and strength 4. These are 4 groups of data here. These are the 4 groups of data. And the null hypothesis is going to be there is no difference between the group or the means of the group and equality among the means. That's the null hypothesis. The counter hypothesis or alternate hypothesis is that it's not same. There are differences here. Okay, and so there are some principles of how we set the null hypothesis. The principles of equality, no change, no effect. For example, new drug, and you want to do hypothesis testing. The null hypothesis is going to be that there is no impact or no effect or no positive or negative effect because of the new drug. No benefit, status quo, no deviation. These are principles behind setting the null hypothesis. SciPy statistical package, for example, these are 3 different groups, and then I'm going to use the one way past the 3 groups, and you're going to get the p-value or t-statistic. P-value here now 0.01 is much lesser than 0.05, so we can reject the null hypothesis. So what does it mean here? It means the mean of these 3 groups are not same. They are different because the null hypothesis says they are same. There is no difference between the means of the group. So that assessment or understanding is wrong based on the p-value that we got. Okay, so you could actually run this on a set of columns, and the visualization, if you want to look at the F statistic, and this is the rejection region, and F statistic here is 0.22, and if that falls under the rejection region, for example, here this is not in the rejection region, so you would not be able to reject the null hypothesis. Let's look at another example here of Mercedes vehicle testing data. In this, we have this data set, and the data set has many columns here, and most of the columns are categorical here. And then one response column, which is the testing time the car actually needs on the assembly floor. So that's the data set here, and we would like to apply a kind of ANOVA here. So let's look at the data here. What does the data actually look like? So all the categorical columns, let's say X0, X1, there are 47 categories here, 27 categories here, 44 categories here. Now these are ideal candidates for ANOVA testing. For example, these are the columns, all 8 columns that you want to evaluate. So just do a scatter plot. By scatter plot, you can see, or a box plot, you can see here the distribution of the vehicle testing time for each of the categories of the car is different. That probably also gives you an indication that the mean would be different across these groups here. Similarly, for this column, is not very different, but okay type. But for column, let's say X4, this is a questionable column, whether the means are actually different or not. Similarly, for X5 also, there is a question whether the means are actually same or not. By looking at this picture, probably it doesn't look like different. Even X8 doesn't look like very different. But visual inspection cannot give you pinpointed answer. So we apply ANOVA here. Okay. So now in this ANOVA, apart from SciPy, stats model package can also help you set up your ANOVA testing. Here we're saying the y, which is basically the response variable, is equal to the x4. This is how you're going to set up. This is almost like linear regression formulation that you need to do here. The ordinary least square is nothing but a linear regression package in stats model. Pass the data frame and it's going to return the p-value to you. And this p-value is 0.04, which means slightly lower than 0.05 or just about 0.05. You can take a call whether you want to accept or reject the null hypothesis. Now, ANOVA test also gives you um, advanced feature. Let's say which groups are actually different. After conducting the ANOVA test, you might want to also look at which pair of groups are actually different from each other in the column X4. So we have these values. So it's called pairwise Tukey test, and it's going to take each of the pair and perform t-tests internally. So here is the A and B, A and C, A and D, B and C, and so on and so forth. So in the previous case, we got here the p-value 0.049. That means we can say that we're going to reject the null hypothesis. That means means are not equal. In X4 column, the means are not equal in the categories. So let's see where they are not equal. Okay, so whether A and B is saying reject equals to false, that means you cannot reject it. That means means are equal here, means are equal here, means are equal for these two groups, means are equal for this two group, here also equal. In the last group, they are not equal. Okay, so that's quite significant, insight into the data here by performing the ANOVA test. You might want to do for all the categorical columns, and you're going to return the p-value. You notice we got p-value of 0.049, right, which is roughly about 0.05. But in the rest of the cases, we have p-value of 0.00, that which is much lower than 0.05. That means we can reject the null hypothesis. And what is the null hypothesis? The means are equal, so you got to reject it. Means are not equal. So means are not equal is good for machine learning because the data is different across the group, and that's what we want. And with the use of ANOVA, we can establish that. These kind of tests are very useful in your exploratory data analysis or feature engineering. I hope you like this demonstration. In the next video, we'll talk about another feature selection and univariate feature selection technique called chi-square. That was a demo on ANOVA. In the next session, I'll be covering the chi-square. See you in the next session. Thank you all for your time.